In the name of God, I am Abdolrasoul Sakhaei Gharagezlou. I am PhD candidate in telecommunication engineering in the University of Tabriz, Iran. The topic of our paper is the sum rate analysis and power allocation in massive MIMO systems with power constraints. There are many challenges in fifth generation telecommunication system due to better services to users. One of the most important existing challenges is energy efficiency and spectral efficiency. Today, the number of users is increasing, which make researchers focus more on energy efficiency and spectral efficiency. One of the methods that can answer these challenges is the use of massive multiple input, multiple output, massive MIMO systems. Massive MIMO system is called a system with a very large number of base station antennas. A large number of antennas in the base station causes uncorrelated noise and a small scale fading to be removed, which improves system performance. One of the important features of massive MIMO systems is low complexity in signal processing, high energy and spectral efficiency, and reliable communications. Since one of the important challenges that can be mentioned in a new system is spectral efficiency, researchers have extensively addressed this problem. We review reference to on behalf of other papers as a research paper. In reference to, the system model is divided into two parts and the total power is divided into two areas according to the distance of users. Users whose distance to the base station is less than half the cell radius are in the first group, and users whose distance to the base station is more than half the cell radius are in the second group. In figure 1 and 2, it can be seen that the proposed method in reference to has a better performance than the existing methods. If Q is the fast fading matrix and components of matrix C are the path loss and shadow fading factors, then the channel matrix between users and the base station is formulated as follows. Equation 1. The precoding used in the system model is the maximum ratio transmission MRT. The MRT vector that is adopted by the base station formulated as follows. Equation 2, where PK is used to show the power of the case user and SK is used to show the symbol sent by case users. The signal received by all users in the system is formulated as follows. Equation 3, where N represents the Gaussian noise vector with distribution of N. The signal received by case user is modeled as follows. Equation 4. The signal to noise and interference ratio SINR of the case user is formulated as follows. Equation 5. Based on the proof which is provided in reference 4, the SINR of the case user is equal to equation 6. The problem that is supposed to be solved is related to maximizing the spectral efficiency of the system, which has two constraints related to the power limitation of users. The sum of users' power should not be greater than a maximum value for the transmission power, and the power of each user should not be less than a minimum power consumption value. The spectral efficiency maximization problem is modeled as follows: equation 7, where C1 is related to the constraint of the maximum transmission power. C2 is related to the constraint of the minimum power of users. Pmax is the maximum transmission power and Pk-min shows the minimum power consumption of the case user, which has a non-negative value. By using this equation transformation, the optimization problem is rewritten as below. Equation 8 and Kp mean equal to this equation. To solve the optimization problem easily, its constraints must be eliminated first. For this purpose, the Lagrange dual function is employed. If phi is the Lagrange dual function of the maximization problem, then we have equation 9, where P represents the feasible power set for users. Lambda and omega represents the Lagrange coefficient corresponding to the constraints of the maximum transmission power and the minimum power consumption respectively. To get a closed form solution of users' power, we use the derivative of the Lagrange dual function. Then we set this derivative equal to 0. I mean equation 10, where k equal to this equation. To obtain the optimal power of users, we write the equation 11 in a simpler way. Equation 11, you can see these slides. Algorithm 1 is presented to numerically solve two desired optimization problem, which maximize spectral efficiency by calculating the optimal power of users and updating the initial parameters. You can see this algorithm in this slide, and you can see the continuation of algorithm 1 is this slide. In this section, the results obtained from the proposed algorithm are analyzed. The results of several scenarios have been compared. These scenarios include the proposed method, game theory method, and equal power allocation method. The proposed algorithm is simulated in MATLAB software. Since the radius of the cell is 500 meters, the distance of the users is randomly selected in these 1 to 500 meters. The obtained results are an average of repeating the proposed algorithm 500 times to provide a stable state of the system. Some important parameters that are initialized are listed in table 1. You can see this table in this slide. Figure 1 shows the numerical results obtained for the desired system in the term of spectral efficiency with the increase in the number of users and antennas. As it is observed in the figure, by increasing the number of antennas, the SE grows. The proposed method has an acceptable performance compared to the game theory method and equal power allocation. This performance improvement can be seen well in the case of k equal to 15 number of users. When k equal to 15, the increase in spectral efficiency is greater than the case of k equal to 5. This point shows that our proposed method provides more significant improvement in the systems for many users. In figure 2, the behavior of spectral efficiency with the increase of the maximum transmission power value has been investigated. As the maximum transmission power increases, spectral efficiency increases. This figure shows that the proposed method has better numerical result than the game theory method and equal power allocation. An important point that can be seen in the figure is the convergence of spectral efficiency for higher maximum transmission power value. You can see the conclusion of this paper in this slide. In this paper, the maximization problem of the spectral efficiency and the suboptimal power allocation of users is discussed. The maximization problem has two constraints, including the maximum value for power consumption and the minimum consumption power of the users. These limitations are first simplified by using a switchable variable change technique and then eliminated by the help of Lagrange dual function properties. As seen in the simulation result, the increase of M and K in the telecommunication cell causes the increase of spectral efficiency value. For the higher number of users, we observe more improvement in the spectral efficiency. For high value of the maximum transmission power, a convergence in the behavior of the spectral efficiency is seen. Based on the simulation results, it is proved that our proposed maximization spectral efficiency scheme has a better result than the game theory scheme and the equal power allocation strategy. You can see the references of this paper that we used in this paper. Thank you.